England. August 1st, 1943. Consolidated B-24 Assembly Line, Fort Worth Division. By mid-1943, the Consolidated B-24 Liberator had become the most produced heavy bomber in history. 18,482 units built across 5 United States plants. Yet United States Army Air Force's field reports already labeled it hazardous upon fuel ignition unarmored wing tanks, holding 2,700 gallons of aviation gasoline, turned small punctures into infernos. In the 8th Air Force, 56% of all Liberator combat losses were traced to fuel system fires. Crews called it the flying coffin. Engineers argued the trade-off: twice the range of the B-17, at half the structural resilience. In missions such as the Ploiești oilfield raids, hundreds never returned, not for lack of courage, but because one 20mm hit could ignite the wing. The aircraft that shattered production records also produced one of the highest burn-loss ratios of the war. How did the Allies' most numerous bomber become its most combustible? At Consolidated Aircraft's design offices, engineers led by Isaac Hemladen presented the Model 32 prototype, designated XB-24. The United States Army Air Corps required a bomber with a 3,000-mile range and 2,000-pound payload, far beyond the B-17's capacity. Strategic planners wanted aircraft that could cross oceans, strike distant targets, and return without refueling. The new Davis wing, a thin high-aspect airfoil, promised speed and fuel efficiency, but offered little internal volume for protected fuel storage. Engineers therefore distributed 9 aluminum tanks across the upper wing structure rather than inside self-sealed bladders housed in the fuselage. The Davis wing represented a breakthrough in aerodynamic efficiency. Its slender profile reduced drag at cruise speeds, allowing the bomber to maintain higher velocities while burning less fuel per mile. But that same efficiency created a structural constraint. The wing's thin cross-section left minimal room for protective measures. Fuel cells had to be positioned between the main spars, directly above the engine nacelles, where heat and vibration were greatest. Archival correspondence to Wright Field, dated January 5, 1940, noted, "Wing storage preferable to fuselage cells for aerodynamic reasons. Self-sealing omitted for weight." The decision reflected engineering orthodoxy of the late 1930s. Before the war, designers prioritized range and speed over survivability. The assumption was that high-altitude bombing would keep aircraft above effective anti-aircraft fire. The reality of combat would prove otherwise. Chief designer Isaac Hemladen supervised a team of 43 engineers and draftsmen. They worked from blueprints spread across drafting tables in Building 7 at the San Diego plant. The prototype's fuselage took shape in adjacent hangars, where riveters assembled sections under arc lights. The first flight occurred on December 29, 1939. Test pilot Bill Wheatley reported excellent handling and a top speed of 273 miles per hour, 30 miles per hour faster than the B-17. Yet even during early trials, ground crews noticed fuel odors in the cockpit after extended climbs. The wing's distributed cell system relied on gravity feed and transfer pumps. Vapor venting occurred through outboard ports, creating a potential ignition path if static electricity or engine heat triggered a spark. Engineers documented the issue but concluded that operational altitude would disperse vapors before accumulation became dangerous. The contrast between expectation and reality was stark. Designers expected clean airflow and cold temperatures at altitude to prevent vapor buildup. They expected enemy fighters to be the primary threat, not ground-based anti-aircraft artillery. They expected self-sealing technology to be unnecessary because hits would be rare. Within 4 years, that design decision would cause over 2,000 aircraft to vanish in flames. By June 1940, the Army Air Corps ordered 7 service test YB-24s and placed a production contract for 36 B-24A models. The manufacturing infrastructure began expanding before the first combat mission. The urgency of rearmament overrode caution about untested fuel systems. Henry Ford's plant, the world's largest, produced a Liberator every 63 minutes. Achieving that speed required simplification, omitted armor plate, thinner skin, and no fire suppression plumbing. The assembly line stretched across 116 acres under a single roof. Workers moved between stations on bicycles. Components arrived on overhead conveyors synchronized to the minute. Wings descended from upper assembly bays to meet fuselages on the main production line. A War Production Board memo, dated April 15, 1942, confirmed self-sealing tanks deemed unnecessary for daylight high-altitude operations. The reasoning reflected pre-war doctrine. Planners believed that bombers operating above 20,000 feet would encounter minimal flak damage. The expectation was that most losses would come from fighter attacks, which crews could suppress with defensive gunfire. Initial optimism masked systemic risk. Test burns at Eglin Field showed vapor ignition spreading across the wing in under 6 seconds. Engineers ignited controlled fuel leaks in a B-24D wing section mounted on a static frame. High-speed cameras recorded the progression. A single spark near the No. 2 tank vent triggered a flame front that raced along the upper wing surface, engulfing fuel cells in sequence. The aluminum skin buckled within 14 seconds. Structural failure followed at 19 seconds. Yet urgency overruled caution. The United States needed heavy bombers immediately. Germany controlled continental Europe. Japan had swept across the Pacific. Strategic bombing offered the only way to strike back before ground forces could be assembled and trained. Production quotas took precedence over design refinements. By year's end, nearly 1,800 bombers left Willow Run. None yet equipped with protection against the element that powered them. The consolidated plant in San Diego added another 650 aircraft. Fort Worth contributed 430. 3 additional plants opened in Tulsa and Dallas. The industrial mobilization exceeded every projection. Workers at Willow Run included women who had never held a rivet gun, farmers who had never seen a blueprint, and immigrants who spoke limited English. Yet they learned the sequences. Fuselage assembly required 1,147 discrete operations. Wing mating added another 833 steps. Quality control inspectors checked every fuel line joint, every electrical connection, every control cable. Rejection rates dropped from 14% in May 1942 to 3% by December. The production miracle came with a hidden cost. Simplified designs eliminated redundancy. Weight-saving measures removed structural reinforcement. Standardized components reduced customization. Every efficiency gain is optimized for quantity rather than resilience. The bombers rolling off the line were identical and identically vulnerable. Engineers understood the trade-offs. Correspondence between Consolidated's engineering division and Wright Field repeatedly raised fuel system concerns. A memo dated September 8, 1942, stated, "Recommend installation of CO2 fire dampers in wing fuel bays. Estimated weight penalty, 400 pounds. Range reduction, 120 miles. The recommendation was noted but not implemented. Range remained the priority. Mass production triumphed over survivability. The logic was numerical. If the Allies could field 10 bombers for every one the enemy destroyed, attrition became sustainable. Industrial capacity replaced individual aircraft resilience as the measure of strategic success. The philosophy worked, but at a cost measured in crew lives rather than factory output. By the spring of 1943, over 4,200 Liberators were in service across 7 theaters. They flew anti-submarine patrols over the Atlantic, convoy escorts in the Mediterranean, and strategic bombing missions over Europe. They hauled supplies over the Himalayan hump into China. They photographed enemy installations and dropped agents behind enemy lines. The most versatile heavy bomber in the world was also becoming the most dangerous to fly. The 93rd and 44th Bomb Groups initiated B-24 combat under 8th Air Force Detachment, 9th Bomber Command. Missions over Naples and Ploiești exposed the aircraft's flaws. The groups had deployed from England in October, staging through North Africa for strikes against Axis supply lines and oil infrastructure. Crews anticipated opposition from fighters but underestimated the flak threat. After-action report number A239 recorded, Ship 42-40369 lost, Fuel ignition following number 2 engine hit. The bomber had been struck by an 88mm shell fragment at 11,000 feet during a raid on the Naples rail yards. The shell burst below the aircraft, sending metal shards upward through the lower wing surface. One fragment punctured the number 2 fuel cell. Another severed a vent line. The fuel-air mixture ignited instantly. Crews described vapor seepage during climb. Ground personnel noticed a persistent gasoline odor in cockpits after engines reached operating temperature. Transfer pumps moved fuel from wing tanks to auxiliary cells during ascent, creating pressure differentials that forced vapors through vent ports. On hot days in North Africa, evaporation increased. The aluminum wing skin absorbed solar radiation, heating fuel to near vaporization temperatures even before takeoff. Despite superior range, 2,100 miles with a 4,000-pound bomb load, and payload capacity of 8,000 pounds, reliability lagged. Operational readiness averaged 64% versus 78% for B-17s. Maintenance crews worked double shifts replacing fuel pumps, resealing leaking cells, and purging vapor from electrical conduits. Every mission generated a dozen maintenance write-ups related to fuel systems. Technical specifications told the story. The B-24D model carried 2,700 gallons of fuel distributed across 9 wing tanks, 2 main cells inboard of the engines, 4 auxiliary cells outboard, and 3 fuselage tanks. The Pratt & Whitney R1830-65 engines consumed 165 gallons per hour at cruise power. That gave a theoretical range of 3,200 miles, but only if every gallon remained contained and usable. Combat changed the calculation. A single 20mm cannon hit could rupture multiple cells. Flak fragments created dozens of small punctures that self-sealing compounds struggled to close under operational pressures. Vapor leaks through vent lines couldn't be sealed at all. And the wing structure concentrated all these vulnerabilities in the space between the inboard engines, where heat and electrical sparks were unavoidable. The 44th Bomb Group lost 3 aircraft to fuel fires in November alone. The 93rd lost 2. Crews began requesting transfers to B-17 units. Morale suffered, yet missions continued. The oil refineries at Ploiești represented the Third Reich's primary source of aviation fuel. If bombing could destroy that capacity, the Luftwaffe would be grounded. Strategic logic demanded pressing the attack regardless of losses. A bomber built for endurance became notorious for fragility. The same range that allowed strikes deep into enemy territory also meant longer exposure to defenses. The same fuel capacity that enabled ocean crossings also meant more combustible material concentrated in a vulnerable structure. Every advantage carried a corresponding liability. Maintenance logs from Benghazi documented the daily struggle. One entry, dated November 23, 1942, read, Aircraft 42-51873, fuel cell number 3 leaking after flak damage. Temporary patch applied. Full replacement required. Another, from December 2nd. Aircraft 42-432. Vapor odor reported by pilot. Vent system inspected. No defects found. Odor persists. The pattern was clear. Self-sealing technology reduced catastrophic fuel loss but couldn't eliminate vapor accumulation. The distributed cell design meant that damage to one tank often compromised adjacent systems. And the wing's location, directly in the flak envelope during bombing runs, guaranteed repeated hits in the most vulnerable area. The next mission, Ploiești, would validate every mechanic's warning. 177 liberators from 5 groups struck the Ploiești oil refineries. Flak concentrations reached 3,000 shells per minute. Of those dispatched, 54 aircraft, 31%, failed to return. Another 31 were damaged beyond repair. Official United States Army Air Forces analysis stated, predominant cause, fuel ignition in wing tanks following light fragmentation hits. The mission plan called for low-level attack to avoid radar detection and maximize bombing accuracy. Formations would approach at treetop height, pop up to bombing altitude, then egress at minimum altitude. The tactic worked. Bombers destroyed 42% of Romania's refining capacity. But navigation errors scattered the formations, exposing individual aircraft to concentrated defensive fire. Technically, the B-24DS aluminum wing housed No. 2 and No. 3 tanks directly over the engines. Shrapnel from flak fused vapor and heat in milliseconds. Survivors reported instantaneous flame front. One pilot described seeing a bomber ahead of him take a single hit near the inboard wing root. Within 3 seconds, the entire wing was engulfed. Within 7 seconds, the aircraft broke apart. German and Romanian defenders positioned 88mm and 105mm guns in concentric rings around each refinery complex. They had studied Allied tactics and positioned batteries to catch bombers during their most vulnerable moment, the pull-up to bombing altitude, when aircraft were slow, predictable, and fully loaded with fuel and ordnance. The 98th Bomb Group lost 13 aircraft. 44th lost 11. The 389th lost 9. Casualty figures told a grimmer story. 310 aircrew killed or missing, 108 captured, 44 interned in neutral Turkey. For every refinery destroyed, the Allies lost half a bomber crew. Tactical reports documented the fuel system vulnerability in clinical detail. Intelligence officers interviewed returning crews and compiled damage assessments. A typical report read, aircraft struck by fragments in the left wing between engines 1 and 2. Fire observed immediately. The wing separated from the fuselage at 7,000 feet. No parachutes observed. Another. Multiple strikes to the center wing section. Aircraft maintained formation for approximately 15 seconds before catastrophic structural failure. The Ploiești raid became the most decorated mission in United States Army Air Force's history. 5 Medals of Honor were awarded, 3 posthumously. Yet the tactical lesson was undeniable. Low-level attacks exposed the B-24's fundamental weakness. High-altitude bombing dispersed flak. Low-altitude concentrated it in the exact zone where the Liberator's fuel system was most vulnerable. Mission planners recognized the problem immediately. Future raids would revert to high-altitude tactics despite reduced bombing accuracy. The trade-off was explicit. Fewer hits on target, but sustainable loss rates. Strategic bombing required attrition the enemy couldn't replace. Ploiești proved that even successful missions could exact unsustainable costs. The success destroyed 42% of Romania's refining output, but at a human cost that forced Washington to reconsider the Liberator's design. Axis fuel production dropped immediately. German aviation units reported reduced sortie rates within weeks. But Allied commanders understood they couldn't repeat such missions. The mathematics were simple. Lose 30% of the attacking force, and the bomber fleet would be exhausted within 4 months. 8th Air Force Headquarters compiled loss rate statistics from 7,000 sorties. The analysis compared B-17 and B-24 performance across identical mission profiles. Results showed B-17 loss rate at 3.7% per sortie. B-24 loss rate stood at 5.1% per sortie. Memo E118/44 summarized. Wing fuel vulnerability primary contributor to excess losses. British Air Ministry observers noted the B-24's Davis wing was efficient in lift, deficient in protection. The statistical disparity reflected fundamental design differences. The B-17's fuselage-mounted fuel cells offered better protection. The B-24's wing-mounted cells offered better range but worse survivability. Combat experiences varied by theater and altitude. In the Mediterranean, where missions often occurred at medium altitude against heavy flak, B-24 losses exceeded projections by 37%. In the Pacific, where anti-aircraft defenses were lighter, loss rates approached parity with other heavy bombers. The pattern was clear. Against concentrated flak, the Liberator's fuel system became a critical liability. Crew testimony reinforced the statistics. One pilot reported, took a single hit in the left wing. Within seconds, flames spread across the upper surface. We had maybe 20 seconds to evacuate before structural failure. Another described watching a formation mate. One burst below him, fragments through the wing. Fire erupted between the inboard engines. The wing folded upward. Then the whole aircraft came apart. The B-17's reputation for ruggedness rested partly on its centralized fuel system. Main tanks were located in the fuselage center section, protected by surrounding structure and separated from engine heat. The B-17 could absorb enormous punishment and continue flying. The B-24, by contrast, concentrated its fuel in the wings where every hit risked catastrophic fire. Defensive characteristics also differed. The B-17's turret layout provided better coverage against fighter attacks. The B-24's nose turret and tail position offered less overlap. Formation tactics evolved to compensate, placing B-24s in the center of mixed formations where B-17s could provide covering fire. Yet the debate remained contentious. Some analyses showed similar or even lower B-24 per sortie losses during specific intervals. Proponents argued that the Liberator's speed and altitude performance offset its vulnerabilities. Critics countered that fuel system fires killed crews faster than fighter attacks, leaving less time for bailout. The faster bomber proved deadlier to its crews. Speed advantages meant little when a single fragment could trigger wing fires. The B-24 could outrun fighters but couldn't outrun its own fuel system vulnerability. Production decisions reflected statistical reality. Despite evidence of higher loss rates, production quotas increased by 40% in 1944. The logic was industrial. Build enough bombers to sustain attrition while maintaining operational strength. The United States could replace losses faster than Germany could inflict them. The strategy worked at the strategic level but offered cold comfort to individual crews. Doctrine shifted in response. Mixed B-17 and B-24 boxes became standard. Revised routes tried to limit exposure windows. Altitude profiles changed to keep bombers above the heaviest flak concentrations, typically below 15,000 feet. Fuel management procedures emphasized early transfer from wing tanks to reduce combustible volume in the most vulnerable area. Commanders faced an impossible calculus. The B-24's range made it indispensable for deep penetration raids. No other operational bomber could reach targets in Poland, Eastern Germany, or the Balkans and return. Yet every mission extracted a predictable toll. The question became not whether to use Liberators, but how to minimize losses while maximizing their strategic value. Ground crews documented chronic leaks. Daily maintenance logs recorded 35 man-hours spent resealing wing panels. Fuel odor in cockpits preceded several explosions. A log entry dated March 14, 1944, stated, "Aircraft 42-52789 lost after takeoff. Fire erupted from the vent port. The incident occurred during early morning operations. The bomber had completed engine run-up and was rolling for takeoff when crew members smelled gasoline. The pilot aborted, but vapor had already accumulated in the wing structure. A spark from the electrical system, possibly a generator brush or a radio component, ignited the mixture. The fire spread too quickly for the crew to evacuate. 5 men died on the ground at their own base, killed by the very fuel system meant to carry them to target. Mechanics replaced ruptured tanks with heavier bladders, cutting the operational ceiling by 800 feet. The retrofit added 400 pounds per aircraft but improved fire resistance by approximately 30%. Yet the modification introduced new problems. Heavier fuel cells reduced payload capacity and range. Aircraft returned from missions with smaller bomb loads or required intermediate refueling stops. Technical details revealed the complexity. Typical European theater of operations B-24s used Pratt & Whitney R1830-65 engines rated at 1,200 horsepower each. They burned 110-octane fuel pressurized to 5 pounds per square inch. Small punctures ejected vapor streams ignitable by static discharge, engine exhaust, or electrical arcs. Transfer protocol directed moving auxiliary fuel early to reduce risk and improve weight distribution, explicitly to lower fire hazards. The B-24D flight manual section instructed crews to transfer to the main system as soon as practicable after takeoff to reduce fire hazards and optimize center of gravity position. The procedure reflected hard lessons from early combat operations. Fuel management became a critical crew skill. Pilots monitored gauges constantly, tracking consumption and transfer rates. Engineers adjusted mixture settings to minimize vapor generation. Radio operators shut down non-essential electrical systems over target areas to reduce ignition sources. Every measure helped, but none eliminated the fundamental vulnerability. Maintenance realities reinforced crew procedures and fuel sequence discipline before and after bomb runs. Pre-flight inspections included detailed checks of every fuel cell, every vent line, every transfer pump. Post-flight inspections documented any anomalies for repair before the next mission. The paperwork trail grew enormous. Each aircraft generated hundreds of maintenance forms documenting fuel system status. One crew chief's log from March 27, 1944, listed, Cell number 4, slow leak at upper seam, compound applied, pressure test satisfactory. Cell number 6, vent line loose at forward connection, line secured. Cell number 7, transfer pump intermittent, pump replaced. The entries continued for 2 pages, documenting hours of work to keep a single bomber airworthy. Ground explosions from vapor ignition were a periodic threat. Unit histories record at least 18 aircraft destroyed on British airfields during spring 1944 from fuel system fires. Some occurred during maintenance when mechanics inadvertently created sparks near open fuel cells. Others happened during engine start when backfires ignited accumulated vapors. A few resulted from combat damage that went undetected until the aircraft returned to base and was parked. Safety bulletins emphasized procedural rigor as survival. One directive dated April 2, 1944, stated, "All personnel will exercise extreme caution when working on or near fuel system components. No smoking within 50 feet of aircraft. No electrical equipment except explosion-proof tools. Fire extinguishers positioned at 10-foot intervals during all fuel system maintenance." Even without combat, procedural rigor became survival. The ground war against vapor hazards proved almost as dangerous as the air war against flak. Maintenance crews wore special non-sparking tools, grounded themselves to prevent static discharge, and worked in constant awareness that one mistake could kill. Flak evaluation officers reviewed gun camera stills showing inner wing strikes and rapid fire spread. The Luftwaffe's Flugabwehr-Aussertung, Anti-Aircraft Evaluation Center, compiled systematic analyses of Allied bomber vulnerabilities. Their reports documented a clear pattern. Liberators were especially vulnerable to hits in the wing section between the inboard engines. Captured gun camera film confirmed German claims. One sequence showed a B-24 formation during a bombing run. A single 88mm burst placed fragments into the left wing of the lead aircraft. Within 2 seconds, flames appeared at the wing root. Within 5 seconds, the entire wing section was burning. The aircraft fell out of formation, trailing fire. It broke apart at 7,000 feet. The Flak Unit 367 recorded an average of 5 rounds per kill on B-24s versus 12 rounds per kill on B-17s. The disparity reflected targeting doctrine. German gunners received specific instructions to prioritize liberators when mixed formations appeared. If a formation contains both types, engage the B-24s first. Luftwaffe analytical file LW.ERF.144/44 stated, "Liberator burns readily when hit in the inner wing section. Recommend concentration of fire on center aircraft of formations to maximize probability of wing strikes. B-17 requires heavier concentration for equivalent effect." The document circulated to all flak batteries on the Western Front. It represented the culmination of 2 years of combat analysis. German observers had studied gun camera footage, interviewed bomber crews who were captured, and examined wreckage to understand Allied bomber construction. The systematic approach yielded tactical advantages. Enemy intelligence exploited the weakness. Targeting orders prioritized B-24 formations. Battery commanders positioned guns to optimize wing strike probabilities. Fuse settings were calibrated for airbursts below bomber formations, sending fragments upward through wing structures. The technical precision reflected German engineering culture applied to air defense. Fire control solutions evolved accordingly. Flak predictor crews calculated lead angles and fuse timings specifically for liberator vulnerabilities. When radar operators identified bomber formations, They reported aircraft type along with altitude and heading. Battery commanders adjusted engagement ranges based on type, engaging B-24s at maximum range to exploit their wing vulnerability, waiting for closer range on B-17s to ensure heavier damage. The tactical shift had a measurable impact. Allied loss rates varied by formation composition. Pure B-24 formations suffered 5.3% losses per sortie during this period. Mixed formations, with B-17s providing coverage, reduced that to 4.7%. Pure B-17 formations averaged 3.9%. The statistics drove operational planning. Allied intelligence recognized the German targeting doctrine through interrogation of captured Luftwaffe personnel. One flak battery commander, captured after D-Day, explained, "We were taught to identify the Liberator by its twin tails and deep fuselage. When we saw them, we knew where to aim between the inboard engines. That's where the fuel is, and that's where they burn." The revelation prompted tactical countermeasures. Formation leaders began varying aircraft positions to complicate German targeting. B-24s no longer flew consistent positions within boxes. Lead aircraft rotated by mission. High squadron and low squadron positions changed. The goal was to prevent German gunners from predicting which aircraft in a formation were most vulnerable. To compensate, Allied doctrine shifted to mixed B-17 and B-24 wings, a tactical admission of unequal resilience. The new formations placed B-17s on the flanks and forward positions where German fighters concentrated their attacks. B-24s occupied center positions with better mutual defensive coverage. The arrangement acknowledged that the Liberator needed protection despite its greater range and speed. Engineers introduced the B-24J with self-sealing neoprene bladders and CO2 fire dampers. The modifications represented the most significant fuel system redesign since production began. Consolidated's engineering team had studied combat reports, interrogated returning crews, and tested various protection schemes. The B-24J embodied their conclusions. Self-sealing bladders replaced aluminum cells in the wing center section. The bladders used multiple layers of rubber and synthetic compounds that swelled when exposed to fuel, automatically sealing small punctures. The system worked well against small-caliber rounds and fragment damage but couldn't prevent major ruptures from direct hits. CO2 fire dampers injected carbon dioxide into fuel cell vapor spaces during combat. The system used compressed gas bottles mounted in the wing structure, activated manually by the flight engineer or automatically by temperature sensors. When activated, CO2 displaced oxygen in the fuel cells, preventing ignition even if vapors leaked into the wing structure. Weight gain totaled 400 kilograms. Range loss measured 120 miles. Tests showed 30% greater fire survival when the protection systems functioned properly. Yet earlier models composed 70% of active inventory. The improved variant would take months to reach operational units in meaningful numbers. Production figures for 1944 showed the scale of the challenge. Output equaled 7,303 units, exceeding all Boeing B-17 production combined. But only 1,800 of those were B-24J models with the improved fuel systems. The remainder were earlier variants with the original vulnerable design. Consolidated change orders listed dozens of modifications beyond fuel systems. Improved turrets, upgraded oxygen systems, better heating, reinforced nose sections. Each change addressed a specific combat lesson. Yet fuel system vulnerability remained the central concern. Even with self-sealing and fire dampers, the fundamental geometry hadn't changed. Fuel still concentrated in the wings directly over the engines in the primary flak strike zone. Engineers debated more radical solutions. One proposal called for relocating all fuel to fuselage tanks, accepting a 20% range reduction. Another suggested armor plating below wing fuel cells, despite the weight penalty. A third advocated for inert gas generation systems that would continuously purge fuel cell vapor spaces with nitrogen from engine exhaust. None reached production. The war's momentum discouraged major redesigns. The existing production infrastructure, 5 plants employing over 60,000 workers, was optimized for the current design. Retooling would have cost months of production at a time when bombers were desperately needed in Europe and the Pacific. Field modification programs offered a compromise. Depots installed self-sealing bladders in earlier model aircraft returning from combat. The work required stripping the wing, removing the aluminum cells, installing new bladders, reconnecting fuel lines, and pressure testing the entire system. Each retrofit took approximately 200 man-hours per aircraft. By November 1944, depot capacity allowed processing roughly 40 aircraft per month. At that rate, converting the entire operational fleet would require 5 years. The mathematics demonstrated the gap between engineering solutions and operational reality. Engineers had answers, but logistics and timing limited field impact before the strategic situation changed. The improved variant came months before Germany's defeat, too late for crews already gone. Casualty statistics told the story. From January through September 1944, 731 B-24s were lost to fuel system fires in the European theater. That represented 3,650 crew members killed or missing, roughly the population of a small town, erased one bomber at a time. 15th Air Force dispatched 178 Liberators against remaining refining capacity. Weather and flak forecasts were marginal. Intelligence reported that German and Romanian defenses had been reinforced since the August 1943 raids. Gun positions now numbered over 300, positioned in depth around each refinery complex. 27 bombers were lost, mostly by fuel fires after flak hits. The loss rate, 15.2%, exceeded even the devastating Ploiești raid 10 months earlier. A captured Romanian report logged, observed aircraft disintegrating mid-air. No direct bomb detonation. Pattern consistent with fuel explosion followed by structural failure. United States Forces Board analysis concluded that 71% of B-24 structural losses originated from secondary fuel explosions. The phrase, secondary explosion, became technical shorthand for fuel system fires. Primary explosions involved ordnance or direct flak hits. Secondary explosions occurred when fuel ignited, generating pressure waves that exceeded wing structural limits. The physics were straightforward. Aviation gasoline vapor mixed with air created a highly explosive mixture. Confined within the wing structure, ignition generated pressure spikes exceeding 500 pounds per square inch. Wing spars designed to handle aerodynamic loads of perhaps 20 pounds per square inch couldn't withstand explosive forces 25 times greater. The wing structure disintegrated, usually within 2 to 3 seconds of ignition. Crews described the sequence in consistent terms. First, a visible flash or flame at the wing surface. Second, rapid fire spread along the wing's upper surface. Third, structural failure, the wing folding upward or breaking off entirely. Fourth, loss of control and unrecoverable spin. From first flash to impact typically measured 15 to 20 seconds. Crews had that long to evacuate, but bailout from a spinning, disintegrating aircraft was nearly impossible. Tactical objectives were achieved, refineries neutralized, Axis fuel production crippled. But attrition rendered such missions unsustainable. The strategic bombing campaign required acceptable loss rates. 5% was considered high but sustainable. 10% was crisis level. 15% meant the bomber force would be destroyed faster than replacements arrived. Commanders began rewriting mission profiles. Height increased. Missions previously flown at 18,000 feet now occurred at 22,000 feet, above the effective ceiling of most light flak. Approach angles changed. Instead of straight-line bomb runs that simplified German tracking, formations now approached from varying directions, forcing defenders to reorient batteries constantly. Venting protocols became mandatory pre-combat procedures. Flight engineers opened vent valves fully during the bomb run to maximize vapor dispersal. Pilots reduced power settings to minimum required for formation keeping, lowering engine temperatures and reducing ignition sources. Bombardiers delayed arming bomb fuses until the last possible moment, minimizing time when both fuel and ordnance were maximally dangerous. The tactical adjustments helped. Loss rates dropped to 9.3% by June, then to 7.1% by July. But the improvements came from doctrine changes, not engineering fixes. The fundamental vulnerability remained unchanged. The B-24's wings still concentrated fuel in the primary flak strike zone. The bomber's range kept it central to the oil war. No other operational aircraft could reach Romanian targets from Italian bases and return. The 15th Air Force's strategic mission, strangling Axis fuel supplies, depended on Liberator range. Yet that same range came from the fuel capacity that made the aircraft so vulnerable. The paradox defined the entire campaign. The characteristic that made the B-24 strategically indispensable, its range, was inseparable from the characteristic that made it tactically vulnerable, its fuel system design. Commanders couldn't eliminate the vulnerability without abandoning the capability. They could only manage risk through tactics and accept losses as the price of strategic effect. Its fuel system kept risk uncompromising. Every mission remained a calculated gamble that fuel cells would survive the flak envelope. Most did. But the 15 to 20% that didn't created the flying coffin reputation that haunted the type throughout the war. An engineering board minutes sheet referenced flame-damped vents and fuel-inerting concepts under evaluation for bomber applications. The meeting brought together representatives from Consolidated, Boeing, Wright Field's Materials Laboratory, and combat veterans with operational experience. The agenda focused on one question: could fuel system vulnerability be eliminated through engineering rather than tactics? Field trials installed flame-dampened vents and nitrogen gas inerting systems on experimental aircraft. The flame-dampened vents used wire mesh screens that absorbed heat from any flame front attempting to propagate through the vent system. The screens acted as heat sinks, cooling combustion below the ignition temperature before flames could reach fuel cell vapor spaces. Results showed pressure drop reduced vapor ignition by 43%. The system worked by preventing flame propagation rather than preventing ignition itself. A spark or fragment hit might still ignite vapor at the leak point, but the flame couldn't spread to adjacent fuel cells. The local fire would burn itself out as fuel escaped, rather than triggering catastrophic wing fires. Nitrogen gas inerting represented a more comprehensive solution. The system tapped engine exhaust, filtered out carbon dioxide and water vapor, and injected pure nitrogen into fuel cell vapor spaces. With oxygen concentration reduced below 12%, combustion became impossible regardless of ignition sources. Tests showed near-complete immunity to fuel fires when inerting systems functioned properly. Memo AFEB 392 documented the findings. Fuel inerting is effective but impractical for mass retrofit. System weight, 280 pounds. Installation complexity, 47 new components. Maintenance burden, significant. Estimated retrofit time per aircraft, 320 man-hours. Estimated fleet conversion time at current depot capacity, 8.7 years. The mathematics killed the proposal. 8.7 years meant the war would be over, won or lost, before even a fraction of the fleet received protection. Engineering had solved the technical problem but couldn't solve the logistical problem. The production and maintenance infrastructure wasn't configured for such extensive modifications. Alternative approaches fared no better. Armor plating below fuel cells would add 600 pounds per aircraft, reducing range by 200 miles. Relocating fuel to fuselage tanks required complete wing redesign and retooling all 5 production plants. Even simple fixes like additional fire extinguishers created cascading complications. More weight meant less payload meant fewer bombs per sortie meant more sorties required meant more exposure to flak. The discussion revealed a deeper truth about wartime engineering. Technical solutions existed for almost every problem. But technical solutions had to fit within existing production capabilities, maintenance infrastructure, supply chains, and operational timelines. A perfect solution that arrived 2 years late was worthless. An imperfect solution available immediately was valuable. Post-war designs, notably the B-29, institutionalized inert gas systems. The B-29 incorporated nitrogen inerting from initial design, not as a retrofit. The system added weight but was integrated into the overall structure, optimized for efficiency, and supported by purpose-built maintenance procedures. The B-29's fuel cells were virtually immune to combat fires. Contemporary literature traced the maturation of self-sealing and inerting technology across the 1940s. Early self-sealing compounds were heavy and unreliable. Later versions used layered synthetic materials that sealed faster with less weight penalty. Early inerting systems were complex and maintenance-intensive. Later versions used simpler onboard nitrogen generators that required minimal service. The learning curve was steep. Engineers in 1939 didn't know what they didn't know about fuel system vulnerability. Combat in 1942 provided brutal education. Analysis in 1943 identified solutions. Development in 1944 proved concepts. But implementation in 1945 came too late for most operational aircraft. Technology existed, but logistics forbade implementation. The phrase appeared repeatedly in engineering reports and planning documents. It became a bitter epitome of the gap between laboratory success and battlefield application. The B-24's crews paid the price for that gap. The innovation abandoned for the Liberator would become standard in post-war bombers. Every jet bomber designed after 1945 incorporated fuel inerting as baseline equipment. The B-47, B-52, and later designs treated vapor space protection as essential as engines or wings. The lesson was written in burning aluminum over Europe. Range without protection multiplies risk. Statistical digests tallied monthly outputs alongside operational losses by theater. The juxtaposition revealed the paradox at the heart of the strategic bombing campaign. Production had never been higher. Losses had never been more costly in human terms. Output peaked at 650 aircraft per month from Ford and Consolidated plants combined. The Willow Run line alone produced 380 Liberators in February 1945. More heavy bombers than Germany had built in all of 1944. San Diego added 190. Fort Worth contributed 80. The industrial achievement was staggering. Combat return rate, however, averaged 91%, lowest among United States heavies. The figure meant that 9% of aircraft dispatched failed to return from each mission. Over a typical 35-mission combat tour, the cumulative loss probability exceeded 90%. Statistically, crews were more likely to die than survive. Official data compiled by War's End showed 2,112 B-24s lost in combat, with fuel system fires confirmed or suspected in approximately 60% of cases. That equaled 1,267 aircraft destroyed by the very fuel that powered them. With 10-man crews, the toll reached 12,670 men, killed not by enemy action directly, but by secondary fires their aircraft couldn't survive. An additional 9,300 crewmen were killed in flight fires that began from other causes but spread through fuel systems. Total fuel fire casualties exceeded 21,000 men. The number represented 2 full Army divisions, or the population of a mid-sized American town, erased from existence because engineering decisions made in 1939 prioritized range over survivability. The paradox embodied United States industrial power versus crew survival. America could build bombers faster than Germany could shoot them down. America could train crews faster than casualties depleted the pool. The strategy worked at the national level. Germany lost the air war, lost oil production, lost the ability to resist invasion. But the strategy offered no comfort to individual crews climbing into vulnerable aircraft. Archival quotation from Air Force Statistical Digest, published 1946, stated, "Maximum production achieved. Loss rate exceeded projections by 37%. Contributing factors: underestimation of enemy flak density, overestimation of fuel system resilience, delayed implementation of protective modifications." The frank assessment came after victory, when honesty no longer threatened morale. During the war, official statements emphasized success. Missions completed, targets destroyed, enemy production crippled. Loss rates were reported but not analyzed in human terms. The Statistical Digest's post-war candor acknowledged what combat crews already knew. They'd been sent into battle in aircraft whose fundamental design made them more likely to die. The comparative frame revealed the scope. Loss rate arguments remained contested in open sources. Various studies showed different numbers depending on time period, theater, and mission profile. But what wasn't contested was that Liberators bore a large share of the long-range burden and paid heavily against strong flak belts. In the Mediterranean theater, Liberators flew 73% of deep penetration missions against oil targets. Loss rates in that role averaged 8.4% per sortie across 1944. In the Atlantic anti-submarine role, Liberators flew 81% of long-range patrols. Loss rates there averaged 2.1% per sortie, lower because German submarine flak was lighter than land-based batteries. In the Pacific, Liberators handled long-range strikes Japanese fighters couldn't intercept. Loss rates averaged 3.7% per sortie. The variation demonstrated that B-24 vulnerability was context-dependent. Against heavy flak, the fuel system became a critical liability. Against lighter opposition, the range advantage dominated. The industrial gamble, range and numbers, succeeded strategically, but at a persistent survivability cost when fuel systems were breached. The United States built sufficient bombers to absorb unsustainable loss rates. Individual units couldn't sustain 15% attrition, but the Air Force as a whole could because replacement aircraft and crews arrived faster than losses accumulated. The strategy relied on industrial capacity as a military asset. Germany couldn't match American production. Germany couldn't train pilots and crews as fast as they were killed. Germany couldn't rebuild factories as fast as bombing destroyed them. The arithmetic favored America, but only in aggregate, not for individual crews. Victory in Europe arrived just as cumulative engineering lessons were ready to be fully embedded in the next bomber generation. The war ended in May 1945. Production of improved B-24 variants with comprehensive fuel system protection was scheduled to reach significant numbers by July. The timing captured the tragedy. Solutions arrived after the crisis ended. Engineers had learned how to build survivable long-range bombers. The knowledge would shape the B-29, B-36, B-45, and every subsequent heavy bomber. But for B-24 crews, the learning curve came too late. They fought with the aircraft they had, not the aircraft engineers wished they'd built. A comparative table contrasted wartime heavies' survivability characteristics and system design notes. The analysis represented the Air Force's institutional effort to learn from combat experience. Engineers compiled data from every theater, every mission type, every documented loss. The goal was to ensure future aircraft didn't repeat the B-24's mistakes. The survivability index used the B-17 as baseline, assigned value 1.00. Every other aircraft was scored relative to that standard. The B-24 scored 0.73, meaning it was 27% less likely to survive comparable damage. The B-29, incorporating lessons from both predecessors, scored 1.12, 12% more survivable than the B-17. Report TS-262 concluded, fuel system design constitutes the Liberator's principal tactical liability under combat conditions. Distributed wing-mounted cells, while optimizing range performance, created excessive vulnerability to fragmentation damage in high-threat environments. Recommendations: all future heavy bomber designs shall incorporate inert gas systems for fuel cell vapor space protection, self-sealing bladders as baseline rather than optional equipment, and structural armor below fuel cells sufficient to defeat standard flak fragments. The report's language was bureaucratic, but the implications were revolutionary. Fuel system protection became a design requirement, not an afterthought. Range would no longer be purchased at the cost of survivability. The B-24's casualties had bought that lesson at terrible price. Post-war reviews emphasized fuel system design as a principal Liberator liability under flak damage, even with self-sealing cells. The self-sealing technology had helped but couldn't overcome the fundamental geometry. Cells distributed across the wing structure meant damage propagated through adjacent systems. Vapor venting through multiple ports created ignition paths self-sealing couldn't close. The wing's position, directly in the flak envelope, guaranteed repeated hits in the most vulnerable location. The United States Army Air Force's Statistical Digest and Technical Histories captured the broader trend toward inerting and self-sealing standardization after 1945. Every bomber program initiated post-war included fuel system protection from initial design. The B-36 featured redundant inerting with triple backup nitrogen generators. The B-45 incorporated armored fuel cell compartments. The B-47 used integral bladders within sealed wing sections. Engineering doctrine shifted fundamentally. Range must be paired with damage-tolerant fuel containment. The two requirements were no longer treated as competing priorities requiring trade-offs. Instead, they became complementary requirements that competent design must satisfy simultaneously. If an aircraft couldn't achieve both range and protection, the design was inadequate. The philosophical change reflected combat's harsh teaching. The B-24 had demonstrated that range without survivability was insufficient. An aircraft might reach distant targets, but if it couldn't survive the defenses there, the range was useless. Strategic bombing required both: aircraft that could fly deep into enemy territory and return despite damage. Captured German analysis reinforced American conclusions. Luftwaffe technical reports studied Allied bomber vulnerabilities with characteristic thoroughness. One document, recovered from Wehrmacht archives in Berlin, stated, "The American Liberator offers excellent range performance compromised by catastrophic fuel fire vulnerability. Our flak doctrine exploited this weakness with considerable success. Future defensive planning should identify similar vulnerabilities in new Allied types." The German perspective validated what American engineers had concluded independently. The B-24's fuel system was a known, documented, systematically exploited weakness. The Axis had built defensive doctrine around that vulnerability. American forces had paid the price. The B-24's shortcomings materially shaped post-1945 bomber fuel system standards. Every subsequent Air Force procurement specification included detailed fuel protection requirements. Contractor proposals were evaluated on survivability as rigorously as on performance. Aircraft that couldn't demonstrate adequate fuel system protection weren't considered, regardless of other advantages. The institutional learning was complete. The Air Force had absorbed the lesson, codified it in regulations, and embedded it in design standards. Future air crews would benefit from protection that B-24 crews hadn't received. The price of that knowledge was measured in burning aircraft and lost lives. A curator's tag listed one of the few surviving Liberators as the Museum Consolidated Postwar Holdings. The aircraft, serial number 44-44052, had flown 37 missions with the 467th Bomb Group. It survived the war intact, one of fewer than 20 complete B-24s remaining by late 1948. Most Liberators met ignoble ends. Thousands were scrapped immediately after war's end. Aluminum melted down for peacetime manufacturing. Hundreds were sold as surplus, converted to civilian freighters or crop dusters. A few became research aircraft or target drones. The survivors represented less than 0.1% of total production. 18 aircraft from 18,482 built. The aircraft in Smithsonian storage bore the scars of combat. Patches covered flak damage on both wings. The No. 3 engine had been replaced after taking fire over Ploiești. The tail gunner's compartment showed hasty repairs to structural damage. The bomber was a physical archive of the air war. Every patch and rivet told a story of survival against odds. Yet the type's strategic footprint was enormous despite modest post-war survival. Atlantic anti-submarine patrols flown by Liberators covered 80% of convoy lanes, protecting millions of tons of supplies from U-boat attack. The aircraft's range allowed coverage far into the Atlantic Gap where land-based fighters couldn't reach. German submarine losses in the mid-Atlantic increased dramatically after Liberator patrols began. Supply flights over the Hump, the Himalayan air route from India to China, sustained Chinese forces throughout the war. Liberators hauled 73% of cargo tonnage over the route. The aircraft's high-altitude performance and payload capacity made it ideal for the mission despite the fuel system vulnerability. Japanese fighters couldn't reach the altitudes where Hump flights operated. Mediterranean oil war missions, despite horrific losses, achieved their strategic objective. Romanian oil production dropped from 600,000 tons per month in early 1943 to 90,000 tons per month by late 1944. The reduction crippled Luftwaffe operations and Wehrmacht mechanized units. German tanks sat idle for lack of fuel while American armor roamed freely. Pacific long-range strikes extended Allied reach across vast oceanic distances. Liberators operating from Pacific Island bases could reach targets Japanese commanders thought safely beyond Allied range. The psychological impact matched the physical destruction. Nowhere was safe from American air power. Production and fielding totals summarized in museum and manufacturer histories quantified the achievement. 18,482 aircraft built. Peak monthly production, 743 aircraft in March 1945. Total service hours, approximately 37 million. Combat missions, over 300,000. Bomb tonnage delivered, over 600,000 tons. The numbers captured industrial might but obscured human cost. Behind each production statistic were workers who built aircraft knowing crews would die in them. Behind each mission statistic were crews who flew knowing the odds favored death. Behind each tonnage statistic were targets destroyed and lives ended, both enemy and friendly. Contemporary assessments observed that the Liberator delivered the Allies required, alongside hard lessons about survivability that directly informed later designs. Air Force historians writing in 1947 noted, "The B-24's service record demonstrates both the possibilities and limitations of strategic bombing. Range enabled deep penetration. Numbers enabled sustained operations. But vulnerability to fuel fires exacted costs that future designs must avoid." The assessment balanced respect for achievement with acknowledgement of shortcomings. The Liberator had done what was asked. It had flown the missions. It had delivered the bombs. It had helped win the war. But it had done so at terrible cost to its crews, and that cost must inform future choices. Museum documentation accompanying the preserved aircraft stated, "The B-24 Liberator served with distinction in every theater of World War II. Its range and payload enabled strategic bombing campaigns that crippled Axis war production. Over 21,000 American airmen died in Liberators, many in fuel system fires that subsequent aircraft designs worked to prevent. This aircraft stands as a memorial to both their sacrifice and the engineering lessons purchased with their lives." The closing assessment was factual, respectful, precise. No claims of glory or tragedy, simply acknowledgement of service rendered and lessons learned. The tone honored memory without romanticizing loss. The B-24 remains a case study in trade-offs: extraordinary output and range, enduring vulnerability to fuel system damage under heavy fire. Engineering students study its design as an example of how competing requirements force compromises. Military historians analyze its operations as an example of how industrial capacity can compensate for tactical shortcomings. Museum visitors see it as a symbol of an era when American industry reshaped warfare. The lesson endured. Range without robust fuel protection multiplies risk. That principle, written in burning aluminum over Europe and paid for with thousands of lives, became doctrine for every subsequent bomber design. The B-24's crews didn't die in vain. Their sacrifice taught lessons that protected generations of airmen who followed. The final lesson was quiet but profound. Technology alone doesn't win wars. Neither does courage alone. Victory requires both, integrated through competent design that protects those who serve. The Liberator demonstrated what happens when design prioritizes one attribute at fatal cost to others. Future aircraft would do better, because B-24 crews had shown the price of failure. If you value fact-based history grounded in archival manuals, official mission histories, and museum sources, consider supporting the channel.